Hey, Bogdan Wrzewski here with another video where we make algebra easy just for you. In this beautiful session, we're going to walk you through how to work with quadratic functions involving word problems. Particularly, the word problems will involve creating an equation of a function that models this parabolic shape when it comes to application. So the word problems would revolve around suspension cable for bridges. So let's dive in. Let's see how we can help you with this question. So in this particular question, the word problem shows that engineers are designing new suspension bridge, right? The bridge spans across the river, and there are two towers at the end. So 200 meters apart is the position of those two towers. And the towers rise 80 meters above the water. So that gives you the height. And this is sort of the width of those two vertical objects. And there's a cable. The main cable is attached to the top of each tower, and it sags to its lowest point 20 meters above the water. So you can start visualizing that there is a vertical line, and there is a cable that would hang down, forming parabolic shapes. Right. And so using these measurements and using this data in the question, the objective here is to find a quadratic equation that models that shape, determine the cable height at the point 50 meters from each tower, and then we'll confirm that the river width indeed would be used as 200 meters. Okay, so let's go. This word problem has no particular diagram. So you can create your own diagram and always think about creating a diagram so that you position the location of Cartesian plane in the most convenient way. For example, on this picture, we just see a sort of rendition of two towers represented by those vertical lines. And then there's 80 meters labeled right here, showing you the height. The distance between the towers is indicated by 200 meters. So we follow the data from the word problem. And there is a cable that attached to the top of each tower, and it sags 20 meters above the surface of water. So the surface of water is the reference point. It would show the location of x-axis. Now, you may say, where's the bridge here? The bridge could be potentially, if this is a road, the bridge could be just the distance across, and then you have to come back to the road. So maybe there is an inclination or not. But the location of the bridge is not that critical. It is irrelevant in this word problem. Our focus is on this parabolic shape. This is the quadratic function that we have to establish its equation and some other points like 50 meters from each towers. How, for example, 50 meters measured from this tower, and you say how high it is the cable above the water surface. Or from this end, 50 meters, what is the height, right, of the cable above the water. So in order to answer these questions, we would have to know the equation of that parabolic shape. So given that the x-axis is lined up with the surface of the water, and because of the symmetry of each parabola, we can say that the y-axis, the vertical axis, goes through the vertex, and this is also the location of the axis of symmetry and location of that y-axis, thinking of a Cartesian plane. So now we have a grid kind of established. We have x, y axes put together in very convenient and most practical way, so that by symmetry, if I label this point 180, and why 100? Because exactly at the center, right in between those two towers, the midpoint would be 0, right? So 100 to the right and 100 to the left. So naturally, in a Cartesian plane context, this point here would have negative x coordinate 100 and positive y. This point here has positive 100 for x value and 80 is for y. So at least we have two coordinates clearly established, but since this is the lowest point on the graph, and we know that x would be 0 here, and the y value is 20, so we have the third point on the graph. And this is a very important, because when we have 3 points, we can find equation of a parabola. You have to have 3 points, or we can have 2 points where one point of the graph has to be a vertex. So that's the sort of requirement. Every time you're working with parabolas, you want to establish equation of that parabola, you have to think of 3 points and you will be good to go, or 2 points with 1 point of those two being a vertex. Now, in this convenient example, we have a vertex. It is given indirectly, but we can make that discovery by analyzing what is given and what is it that we need to do. So generally speaking, you would say, okay, this is my objective. I have to find the equation of that y is equal x squared, ax squared plus bx plus c. Since point 180 is established because it's given for sure, the other one is given as well because by the symmetry, and then by reading the question, the lowest point is 20 above the water surface. So at 0, we can introduce that point. The y coordinate is 20. So now we have 3 coordinates for that quadratic equation, or for quadratic functions in particular. And we can determine that the value of the c, the constant, is 20. Because when x is equal to 0, y is equal to 20. So that already simplifies this equation. And we know that by doing other questions about parabola, that since the vertex is on the y-axis, the equation of the parabola is reduced to y is equal to ax squared plus c. So that sort of takes care of that b middle term is equal to 0. So the vertex, now we concluding, it is established, it is located at that coordinate. We have 2 other points, so it's a beautiful setup. Let's go and do the calculations. So now we have the list of 3 points. Bingo, we know this. Parabola is opening up because of the sort of context of the word problems. The cable sags towards the surface of the river. It hangs from 2 points. So we have this beautiful equation of parabola to work with. 20 has been established. Also, just a quick reminder, coefficient a can never be equal to 0. So we must be aware of that. To find the coefficient a is the very important step, and we have to utilize any of coordinates of the points that we know. For example, 80 is equivalent as y coordinates to point 100. So we're going to use this and plug into this equation where c is already figured out. X is 100. So you put inside of that equation x 100, and on the left side you have 80. So this is an equation that you have to work towards finding the value of a. So because x is to the power of 2, then thinking of the BEDMAS rules, raise it to the power of 2 to get 1000, right? Plus multiplication is important here because a times 100 squared, and that coefficient 20, at the same time, you can shift it over to the left side so that you get 60. So hopefully this makes sense now. We did simplify this equation by thinking of the bed mass, and we applied the exponent first, and we moved at the same time that constant value 20 from the right side to the left side. That is established right here. So solving for the coefficient a is simply to divide 1000 into 60. So 60 over 1000, you get that coefficient a, which tells you that really the cable suspension is a very wide parabola because the leading coefficient is very tiny and the c value is 20. So we have this beautiful equation, and having that equation allows you to solve for any point on that parabola. So when they said in the question, find a height, 50 height of the cable above the water surface, 50 meters from each tower. So if you recall the diagram, you go from the right side tower 50 towards left, or you can think of the left side tower and moving 50 away to the right. So either you can use positive 100x and 50 for y using this equation, or you can substitute x is equal to negative 100, negative 50, I'm sorry, and to find the height of the coordinates. So knowing that the symmetry of the parabola allows you to determine that 0.50 along x-axis is either from 0 towards the right or from the point 100 moving to the left. So positive x 50 or negative x 50 would produce the same results to find the height because of the symmetry of the graph. So plug in 50 into the equation and find the height. So y is equal to 35 when you do the math. You would raise that to the power of 2, 50 times 50, 2500 times this very small numbers, 6 over 1000, and then add 20, and voila, 35 is the location that represents the height of the cable above the water surface. So confirm the symmetry and span. Knowing that the parabola is already symmetrical and the axis of symmetry at the vertex, we already see this symmetry because of the fact that we have created a diagram that shows negative 100 to the left, positive 100 to the right, and at 0, you can sort of see this on the diagram, there is an axis of symmetry. So if the towers are located 200 meters apart from each other, so the width of the river technically also would be comparable to that number. So they want you to sort of confirm that the width of the river is in between those two towers, so it cannot exceed as 200 meters. So hopefully that makes sense. So because of the symmetry, we conclude that the river width is also 200 meters. So now we were able to answer all those questions given in the word problems. We created a diagram, we identified given points, we identified that one of those points given is a vertex, so that gave us the coefficient c. We used the standard equation to find the coefficient a in the process of substituting one of the points, and then eventually we found how high is the cable 50 meters from either end of the tower. If this question makes sense to you, then you proceed to do the practice questions. That's the part of our lessons. We ask you to do the practice questions so that you can implement the skills right away. Thanks for watching. We'll see you next time. Bye for now.